PJS. Math exams. You should blow off your math exams and focus on CSE 116. What's up, Bite? UB Alex. UB Marcos. Zianatri. You can't see me? You should be able to. Yeah, P, try a refresh. I mean, that's always the answer. Mango Mutiny, I feel ya. I was up late last night getting some work done. I might yawn a few times. Ellipso, what's up? Oh, 1 minute in already. Alright, let's get into this. P. A little bit much there, but sure. PJB, I still want to look at the data. I was trying to find time to do it over the weekend, but something else came up I had to take care of. So I didn't get to go through everything like I wanted to. But hopefully tonight I'll look through. Everyone who got an email that said you're at risk of failing, I'm at the very least going to look through all of them. See how they did. Hopefully, hoping it's good. Just anecdotally, I think it went well that a lot of students did catch up over makeup week. But hey, it's time for the return of lecture questions. So hopefully everybody did get caught up quite well because, the course is gonna, of course, keep moving on. We're halfway through the lecture questions. So during makeup week, that was right in the middle of all the lecture questions. We had exactly half of them released. So the other half is coming, one lecture at a time, one question every lecture, until they're all released, until the end of LO5. So they're coming. So hopefully you're done with the first half of the lecture questions, because the second half, there's no stopping it. There's no stopping the lecture questions. So with that, I feel like I've talked about this before, but I'll talk a little bit about lecture questions right now. Is the reason for lecture questions to exist is to help you and guide you as you're learning the material. There was a time before lecture questions. I think of that as before the dawn of time. It was dark times before lecture questions. But before lecture questions, it's 5 homework assignments, and that's it. Just think about trying to jump into one of those homework assignments without even looking at the lecture questions, without getting that little bit of guidance to help you out. Same with 115. There was a time before UB Infinite where we would just throw you in a lab exam and say, I hope you studied the lectures and hopefully you practiced, because, we would just throw you in it and, students would fail. So the lecture questions, if you can't do the lecture question, at least it's an early warning sign like, whoa, maybe I don't have a good enough grasp on this to really get through all the material and get through the assignments. Because lecture questions, I don't think anyone would argue against me if I said lecture questions are way easier than the homework assignments. So getting the practice with the lecture questions gets you ready for that homework assignment a little bit. And even then, students say that there's a big jump, especially the states questions, that there's a big jump, and there is. You're definitely right. From the 3 state lecture questions to the state homework, there's definitely a big jump up in difficulty. Have I ever used Windows Linux? I'm not quite sure what that means. But is that like the PowerShell or yeah, there goes my yawn. Or like this thing. I don't know what UB Linux exactly is. I might use it and not even know that that's what it's called. The algebra lecture question is tough. Yeah, private Piazza post. If you don't get an answer with your private Piazza post, try rewording your question. You'd be amazed, or maybe you wouldn't, at how many private lecture questions on Piazza we get that are just, here's my code, help. You are probably not going to get a response. In fact, I'd say my TA shouldn't be wasting their time on questions like that. Those are, maybe in office hours. Even then, it's not very appropriate. But if you have very specific questions, like I've reviewed the lecture for this lecture question, I've watched the video, and I just don't understand how to apply this part. Like, it makes sense when I see it in lecture, but applying it to the lecture question, I'm just not quite sure how to do that. You word a question like that, you're going to have like 3 TAs and maybe myself answering that question. But if you're just like, it doesn't work, help. I would guess that's what your question amounts to. Unless you just posted it now. But if you posted it when that question was up, when that lecture was relevant. Try posting again when rewording your question with more detail. Do we have a TA interview this week? Wow, I'm actually completely blanking. Check your email. I'm completely blanking on that. I don't think so. I think it's just makeup interviews this week. Is that true? Since last week was makeup week, there's really nothing to test you on. I think it's just makeups. Anyway, let's get into this. I'm already 5 minutes in, so let's do this. Lecture question. Lecture questions are returning. And here's the next one. So we're still banning var. We're back in functional programming in LO3. So we're banning the keyword var and expecting you to use the collection methods that we'll talk about today, and also returning a function. This is something we haven't done yet, is returning a function. It's the last piece to first order functions that I want you to have a little practice with. I keep saying that functions, you can use them anywhere that any value in Scala is used, and that's using them as parameters, storing them in variables, and returning them from functions. Are the three things that I keep mentioning. I gave you lecture questions for the first two. Now I want to give you a lecture question on the last one, returning a function. This is critically important for your homework. You'll be returning functions and calling functions that are returned and things like that. So I want to give you practice with that. So to that end, give me this method average in range. And I've had a lot of confusion on this last semester, so I want to try to clarify it. I added some more text here, an example, just to make sure we all know what this is asking, to hopefully avoid that confusion. But we're going to take a list of doubles in this function average in range and return a function that takes two doubles and returns a double. And the function that's returned should compute the average of all the values in this initial list of doubles that are between these two doubles as parameters. So these two doubles that this function that you're returning takes are the endpoints of the values, the min and then the max, and returning the average of all the values in that list that are between the min and the max. So you should be checking when you get these two doubles for each value in the initial list, is it greater than the first parameter and less than the second parameter? And exclude equality. Not that it really matters because these are doubles. Doubles are not reliable equal anyway. But use strict inequalities, not inequalities that include the endpoints. Just because that's what I did in my solution. If you do the same thing, you're not going to have any strange Autolab issues. So use strict inequalities. And give me the average of the numbers that are between those two values. So if this is our initial list, so we call average and range on a list with these values. And then the function that's returned from average and range, we call that with the inputs 1.5 and 4.9. We're going to go through this list and check for each value, is it between 1.5 and 4.9? 1 is not, 4 is, 2 is. I should have put those in order, mixed up the order. 5 is not, 3 is. So we're going to take the average of 4, 2, and 3, and the average should be 3. So if I call average and range of this list, that gives me a function. I call that function with 1.5 and 4.9. That should return 3.0. And just like any lecture question, whenever I give an example like this, that better be the first test case that you write up. It would be wise to do that. And then add more test cases as you go. And then, of course, testing. Testing is, I'd say this one is pretty equally weighted in writing the thing and then testing it. I want you to get experience with both sides of a method that returns a function and using that function that's returned and getting used to just functions being regular values in your programs. This is something critically important to homework 3, as I mentioned. You're going to be on both sides of this. You're going to be calling methods that return functions and expected to be able to use those functions. And you should be able to write methods that return functions. And yeah, mundane madman. Yeah, this should handle negatives. There's nothing in here that says they all have to be positive. Just for the example I happen to come up with on the spot, I used all positive values. But there's nothing in here that says they can't be negative. Yeah, P, you're here every day. You know the view count is crazy low. We started with 229 students. Quite a few of them officially resigned, so we wouldn't expect any of them to show up, but it's still depressingly low view count. My optimistic side says a lot of them are just watching the VODs on YouTube. Maybe they want to watch me at 2 times speed and skip around the video. Students like to do that, but I have my doubts that that many students are. I mean, we're at less than half after resigns, which is typical for a course that doesn't take attendance, unfortunately, but it is what it is. Why do you think we needed a makeup week? So much of the class isn't even keeping up on lectures. Can't even sit there and watch a video. It's possible to fail a homework interview. Yeah. Why would we do interviews if they were just going through the motions? All right. Oh, yeah. Yeah, we look at the interview results, the head TAs and myself. Mostly the head TAs, they'll take the main pass, and then I'll do a few spot checks to make sure what they did makes sense. But yeah, they'll decide, and based on what the interviewing TA reported to us, I'll make that decision. For homework interviews, if you did the homework on your own with, honestly understanding what you were doing, it's pretty hard to fail that interview. But if you got outside help, you're probably going to fail that interview. All right, so let's talk about sorting one last time. And yeah, read the syllabus. Thanks, P. Sometimes I feel like an ass when I'm like, dude, read the syllabus. The answer to your question is in the syllabus. But sometimes the students can say that for me, and I don't have to be the ass. But just read the syllabus for a lot of the questions that I get in general. I don't know which specifically one you're referring to right now, but a lot of the questions I get are just read the syllabus. How do the application objectives go? Do I have to do just read the syllabus? It's not that much text. So one last sorting example. We saw a lot of sorting examples. We saw custom comparators. We even broke apart sorting functions and algorithms to see how they work. For a couple of them, we saw merge sort uses a comparator and recursion to get n log n sorting. But I have one new question. Like, if I gave this to you as a lecture question, like, how would you even approach this thing? So I say we can do any type of sorting that we could ever dream up with this custom comparator that we can write. But what if we had this as a lecture question? Write a method that takes a list of points, of 2-dimensional points, and sorts them based on their distance from some reference point. So I have a cluster of points, and I want to sort them based on their distance to the point, let's say 3, 4. And I want to change that point no matter what. Like at runtime, when I call this method, I want to be able to change that point. So your method should be able to take a list of points and a reference point as parameters and sort based on that reference point. How would we approach something like this? So what we would like to do, our strong temptation would be to have our comparator take 3 parameters. We have a comparator that compares 2 points, and we'd like it to take a third parameter, which is the reference point, so we can compare to that reference point. But we can't do that because our sorting methods, and Scala's sorting methods in any language, the sorting methods are going to be using the protocol where you take 2 instances, 2 objects of the type that you're sorting, and compare them with that comparator. That comparator has to only take 2 parameters. That's it. That's the protocol. That's how we wrote our merge sort, and we're not going to say, okay, you want to add a reference point, a third parameter. Let me just rewrite merge sort to accommodate your third parameter. Not going to happen. You're not going to find any standard libraries that do that. So we seem to have an issue here where we need that third parameter. And our answer here, and the answer in the lecture question, of course, it's leading into that, is to make a function dynamically with the additional parameter built in, or I'll sometimes use the phrase baked in to the function that we create dynamically. So if we have, say, some distance function, we're just going to compute the L2 distance between 2 points, the square root of the sum of the squares of the differences in each dimension. Our comparator can only take 2 physics vectors, but we can write a method that returns a function that builds our comparator with the reference point baked into it. So I want some method that's going to create my comparator, called distance comparator in this, takes that reference point that I want to sort by. So I want to sort by the distance to some reference point. This method is going to take in that reference point as a parameter and bake that into a function that follows the protocol of my comparator. So the comparator takes two physics vectors and returns a Boolean like we've seen. We're going to return a function that takes two physics vectors and returns a Boolean that follows that protocol, so we can use it with all our sorting methods. And then we're going to take this reference point and just put it right into our function. So this is going to say if the distance of the first point to the reference point is less than the distance of the second point to the reference point, then return true. The first parameter or first argument goes before the second one. So this reference point is built into the function and kind of serves as a third parameter, but we build that in through a method that takes that third parameter and returns a function with that parameter in there. So we can create dynamically a function with any reference point that we want. If we have 8 different reference points, we want 8 different comparators for all of them, we're going to call distance comparator and create those functions dynamically at runtime when the method is called. We're going to create this function, return it, and then use that for our comparator. So this gives us a lot more power. We can have a lot more flexibility. So our sorting methods can still just take two physics vectors, but we really have pretty much unlimited functionality here. We can create these functions any way we want. Even though they take two parameters, we can build in a lot more information into these comparators. Can I explain it? Can you return it? Explain it slower. It's like mixing functions. Is 250 offered in the winter? No, I almost certainly know. It hasn't been in the past. I doubt it is this winter. You don't want to do 250 in a winter. Isn't that like 4 weeks? You don't want to do that to yourself anyway. And no one would want to teach that because everyone would fail. It'd look bad. Yeah, I can't always just slow down. And that is one reason why I try to not let the viewer count affect me too much. Is maybe there are students who just want to watch the VOD. I use the example of ×2 speed, but there might also be students who want to watch it slower. They want to rewind a few times and stuff. If you just can't keep up with the pace that I talk, I mean, I got a lot of stuff to cover. Usually I got to talk fast. Today is a little more laid back lecture. There's not a ton of content here. But usually I'm talking at warp speed. So, but we take a parameter. We have a method that takes a parameter and returns a function that uses that parameter. So this function doesn't take in this reference point that we're sorting by, but it does take two physics vectors and compares their distance to the reference point. So we're creating a function by using this parameter of the method. So we're mixing method calls, function calls, and creating functions all in one example. So the usage of this, if we have some reference point that we want to sort by, we want to sort a list of points. Assume points is some list of points that physics vectors that I've already created. We want to sort them by their distance to the point 0.5 in 0. I'm thinking two-dimensional space here. And then we can call our merge sort function by calling the distance comparator method with that reference point. This reference point in this case is going to be 0.5, and compare the distances of any 2 points as we're going through the merge sort algorithm to their distance between their distance to this reference point. So our comparator is the function that's returned from the method call distance comparator with whatever point we want to sort by. Explain yeah, looks like P explained it for you. Explain parameters again. Parameters are whatever a method takes or a function. The other side, arguments, that's what the actual values that we give when we're calling a method or a function. In this case, the constructor method for physics vector. Reference point, that's an argument to the distance comparator, and then we always assign the parameters to the arguments. So I'm calling distance comparator. I have this parameter reference point, which is a variable of type physics vector that I'm creating, and I assign that equal to the argument that I'm calling that method with. So reference point is the value, and then it's assigned to the parameter, and then that parameter is used throughout the method. And same with functions. This function takes two parameters, v1 and v2, and then inside the merge sort that we saw 2 weeks ago, inside that method, we're going to call this function with arguments and assign v1 and v2 specific values, and then execute this code inside the function. Like a function inside a function, kinda. So when we call distance comparator, it's returning a function, and then in that function, we're using that function here. So I could also expand this. I could say val f of type physics vector to Boolean equals distance comparator of reference point, and then merge sort of points in f is the function. But the function is just a value that's being passed around our program that we're returning. That's the return type of this function. The return type of this method, the return type is a function that takes two physics vectors and returns a Boolean, which is the protocol for our comparator functions for our sorting methods. So yeah, we got a bunch of layers here, and we're kind of reviewing the first week of, since that was 2 weeks ago, the first week of functional programming. But we have a method that takes a function, and we also have a method that returns a function that's used as the input function of the merge sort. So as the name implies, functional programming, we're throwing functions around all over the place. We're using functions in complex ways to be able to get some really unique functionality. Like before with object-oriented programming, we would have our distance comparator be a method that takes advantage of a state variable, which is the reference point. This is the functional way of doing the same thing. And we could use global state, but you shouldn't in general. Oh, Grudge, change your name. I mean, I have to call you Trino. Trino! Okay, so let's shift gears into collection methods. And here I'm going to give you a bunch of examples of methods that we can use with our collection, specifically lists. And this is kind of just one after another, example after example of just some cool built-in methods that you can use with Scala. So for this, we're not necessarily learning a new concept. We're still just using first-order functions and exploring some of the methods that are built into Scala that use first-order functions. We're going to see some cool things that you can do with Scala. These are very important for your homework, for the genetic algorithm homework. You're going to need to use a lot of these collection methods to be able to complete that homework without using the keyword var. So you can, like these methods internally are going to use var, but we're going to use them and call them in a way that that we don't have to use var, but the methods are going to. But in short, I'm banning var just to force you to use recursion and also these collection methods, so you can get a lot of practice with first-order functions and recursion and get a feel for what functional programming is all about. So these collection methods, you can certainly use them even though internally they use the keyword var, but this is how we're avoiding using it ourselves. And we're avoiding the spirit, like the purpose of having variables in our code. We're going to call these methods so we don't have any changing state in our code. So let's rip through a bunch of these. You already finished genetic algorithm? Are you asking me? I did. Mango Mutiny did, though. I already completed the homework. Now I get to see why I'm dumb. Well, you had to have used some of the... I'd be interested to check that out. I might check that one out. Is if you didn't use any of these methods, any of this functionality, and still got the assignment done, I'd have to see that. I don't know if that. I won't say it can't be done, but I can't think of a simple way that you could. Anyway, let's just get into this. Yeah, and you're definitely not dumb, especially if you finish the homework. So let's go through these. For each, the simplest one, obviously why I'm starting with it. But on a list, if you call the for each method, this is going to be just like using a for each loop. You're going to execute the function given to the for each method. For each takes a function that takes as an input the input type of the list and returns unit. And then calls that function for each value in the list. So if I say, instead of saying like for word in words, print line word, that's how we would do this using a loop. Here we can kind of flatten out that loop and write much more succinct code, which for all of these methods, you're going to start seeing some a lot more succinct code, a lot more expressive code where we can use, one line of code to replace what normally would take us, 5 or even 10 lines of code. And you'll see that for your homework. When you're done with the genetic algorithm homework, or if you're Mango Mutiny, you should look at your code and see not a ton of code and not a lot of lines of code, but you'll be able to complete so much with those lines of code, including my solution. I wrote a genetic algorithm with using var and then without using var, and my number of lines were cut in at least half, maybe even more. In my whole genetic, I'm not going to say the number of lines. I always get in trouble with that. My TAs yell at me, "You said your genetic algorithm was X lines. Now every student thinks that theirs has to be X lines, and they're trying to figure out how to do it." Doesn't always, and then it just distracts you. It makes your homework harder because you're trying to match what I did in my solution. Isn't for each kind of against immutability? No. For each would have been against... for each would have been against state, where we were doing no control flow. But for each is if you're updating a variable. So if you're doing like the accumulator pattern like we did in 115, that would be against the spirit of immutability. And not even necessarily against the spirit, but against the spirit of how we're doing immutability in this class. If you have local variables that are changing, it's not that bad for immutability, even though I do ban that in this class, but I'm doing that for different reasons. So for each, this is useful, but not too useful, to be honest, because... with this, of course it is against the spirit of immutability. For each specifically. Yes, it is against the spirit of immutability. That's my next bullet point. I forgot. I was about to say it. Because for each takes a function that returns unit, the only reason you would ever use for each is for the side effects, which is to change some state. In this case, we're changing the state of standard out of the console, which isn't the worst thing. But what else would you use this for? If you had a list of objects and you wanted to call some method on all those objects that modifies its state, that's another case where you'd use for each. But for functional programming, not too useful. The next lecture is all about immutability. The next two lectures, actually, it's all about immutability, which is a word you might not, you'll learn about it Wednesday if you don't know what that means yet. It means the state can't change, in summary. That's the TLDR. So not very useful if your objects are all immutable. Strings, for one, are immutable. So let's get on to some that we'll actually use. Filter, this is like Monday's lecture question. Lecture question 3-1. This is effectively, kind of what I had you write, but I changed it a little bit just so somebody who already knew about filter couldn't just do .filter and get that lecture question done. So I had it work with maps and then filtering values based on their keys, based on the values of their keys. So this will take a Boolean function, a function that takes the type of the data that we're iterating over and return a Boolean. And so in this case, I'm going to check if the length of the value is greater than 3, then we're going to keep it in this list. So we're going to filter out anything for which this returns false. And again, I'm using this underscore syntax. You're going to see this a lot today. I'm using this just to condense the code on the slides and get things a bit more succinct. This underscore is the way of creating a parameter list and using that parameter without explicitly having to say that this function takes a string. We could name that string something like s, and then say s.length greater than 3. And with the big arrow notation, we could do that. We certainly can. And when we get to IntelliJ, I might expand some of these and just show you the difference. But if we're only using a parameter one time, we can skip the whole declaring of parameters. We can skip the parameter list. We can skip the big arrow and just say underscore in replace of the one time that we're using the parameter, and then write our function, just the body of the function. So we're only providing the body of the function, and underscore is used in place of the name of the input. You can't use mutable. Do it small. Come on, that's obviously not. If I'm teaching you, well, maybe that's not obvious until Wednesday's lecture. But if I'm using, if we're embracing immutability and you just use mutable and cheese everything, obviously you haven't learned anything about functional programming. Immutable is, I mean, in my grader it's banned, but it should go without saying. If you're using a mutable list buffer or any mutable data structures, you're completely defeating the purpose. Because you could have a mutable list buffer that you only use to store one value, and then just change that value and use a mutable list buffer as a variable. Like, you can obviously get around the entire spirit of the assignments. So of course that's banned. So let's look at let's look at some more of these. Map. This is what I used to have a lecture question where you write a map function, but I got rid of that. I changed it to the filter one. But this takes a function and returns a new data structure with all of the values of the original data structure, but with this function applied to it. So here I have some list. I'm calling the map method of a list, and I'm mapping all of the inputs, the list as inputs, putting them through this function, which I'm going to take the square of each input, and creating a new data structure with the output, with the return values of that function on each value of the list, and maintaining the order of the list. So I'm going to call this function on each value in the list and return a new list. If I use my for each, I'm going to use that just to print them to the screen without using 3 lines. Print these all to the screen, and of course I get the squares. This number squared is all of the squares of the numbers. So notice, of course, the reason why we're going through all this, or at least your reason why we're going through all this, we can't use var here. How would you do this if you're not using the map method? How would you do this without using the keyword var? Like, normally we would create an empty list and keep appending to that list until we have our full list of numbers squared. Here we're doing the same thing, but we're not using a var. So I say that's for your purpose. For my purpose, banning var is just my way of forcing you to use things like this so you can get more practice with first order functions. But that's how you're going to get around my restriction. You're going to use these things. That's what I'm pushing you towards. So no var here, but we did something that if I gave this as a lecture question last week or 2 weeks ago, you would probably say, how the hell am I going to do that without the keyword var? Here's your answer. .map, give it a function, and then .map is going to have the accumulator in it. If we crack open that and look at how map works, it's going to have an accumulator with an empty list and everything. But it's out of your code. If it's not in your code, and it's not breaking the spirit of what I'm doing, you're still using first order functions and recursion, then it's cool. So we got that done without using var. If lists are immutable, why don't we just call them tuples? I mean, that's just what Python calls them. Why doesn't Python call them immutable lists? It's just different names in different languages. I'm sure there's other differences. There might be other differences that I'm just not aware of, but just different different languages. .fill and .tabulate. Not familiar with those off the top of my head. Do it small. There's tons of these. I'm giving you examples here. There are tons more. You can go to the Scala reference and find all of... Just go to the list class and you can see all of the... you can see all of the things. All of the methods that you can call. So map, you can also change the type of the output. So if I have a list of strings and I want to convert this to a list of ints containing the length of each one of those strings, no problem. Map can do that. And in this case, all the types were inferred. .length returns an int, and my list words is of type string. So it's inferred that this is a string, and it's going to return an int, so it's going to be a list of ints. Scala is able to handle all that for us. It is crazy powerful. You can get, that's what I mean, you can get a lot done with very little code once you start embracing these things. It's one of those things that it's just so nice, so powerful, so satisfying to use these things. Where you would normally, like, to do this, you're using at least 5 lines, you're creating an empty list of ints, you're iterating over this list, and then appending to the new list that you created for each of those values. Here, just one line, just where's that map, .length, done. Moving on. Yield, a lot of requests for this one since I used it in the anagrams example. Yield is doing the same thing as map, except it's using a little bit different syntax. I should say it's doing something similar. There are of course differences. But this is doing something very much the same thing, except we're using the for loop syntax. So we're using a for loop, iterating over values, and putting this keyword yield right after the start of the loop and right before the body of the loop. Put this keyword yield here, and what this is going to do is collect all of the values for each iteration of the loop by treating this, you can think of this as a function call in the sense that the last value the last expression that's evaluated is going to be kind of the return value of each iteration of the loop. All of those values are collected into a new data structure, and then that data structure is returned. So we can actually assign a for loop like this and get, with the keyword yield, and get a new data structure with the body of this loop applied to all the inputs of that. So this is nice if you need to do something more complicated that just the syntax would look a little strange if you used map. If you tried to do something really complex in here, you might want to expand it out a little more. You could create a function, store that in a variable, and then put that in the map. You know, there are other things you can do. But sometimes, just mostly based on preference, it's nice to just use the keyword yield and then put all your code in this code block instead of creating that code block in a function and then, you know. So it's a little bit different syntax. Plus, you can iterate over, you know, anything you can iterate over, you can use the yield keyword for. So here we're doing the same thing. We're taking this list, we're squaring each number, and then collecting them in a data structure. You know what? Maybe this is easier to read too, since you're used to for loops. You just add this keyword yield in here. And fun fact, I don't talk about this in the class. I'll mention it briefly right here. A conditional, an if statement. If you say if some block of code, else some block of code, throw some else ifs in there too, that will also resolve to the value of the last expression that's evaluated. So you can actually do the same thing. I can do like val x of type int equals if something, some code, else some code. You can actually assign the result of an if statement. A conditional will resolve to whatever the last thing expression that's evaluated is. Same way as a function. So you can say equals some conditional as well, equals some for loop, which doesn't really make sense unless you use the keyword yield. But with a conditional, you can do it without any extra keywords, any extra syntax. It's something you've always been able to do. Yield will try to match the type of the data structure that you're iterating over. This isn't always possible, so it's going to just get close in some cases. If you're iterating over something that's not matching the type of the data structure you need to assign to, for this course, we mostly stick with list. If you need a list, but you're iterating over something that's not a list, so this 1 to 5 is going to return a data structure of type range, and then Scala is going to try to yield something of type range. It's going to get close. It's going to return a sequence in this case, which we can't assign to our list. So in some cases, you have to take the return value. What I do is wrap parentheses around this entire thing, the entire for loop. So this resolves to a data structure, the entire for loop. That returns to a data structure containing the values 1 to 5 squared. As a sequence, wrap that whole thing around. I have this sequence inside these parentheses, and I want to make sure that sequence evaluates first using parentheses, just like in math class. We use the parentheses, make sure that evaluates first, and so I'm not just calling something on the body or whatever, however Scala is going to interpret that. I like the parentheses, it makes it clear. And then call toList. Just convert that sequence into a list. So I slap a toList on that, and now I have that as a list of doubles, and then I get the same values that I had before, using a little bit different setup. There's between iterable of string and a string. Not sure what you mean. We can talk about that after the lecture. Maybe you can give me some follow-up info. Between an iterable of string and a string? Like, you just mean a data structure of strings versus a string itself? Next up, reduce. I told you, this is just one example after another. There's no new concept I'm covering right now, so it's just showing you what you can do with what you already know. So it's kind of just one after another. Here's the syntax for this cool thing that you can do in Scala. So reduce is the next one. This one gets a little more complicated, a little more powerful, a little more exciting in my opinion. It's going to take a function that takes two values of the type of the list that we're using, takes a function that takes those and returns a single value of the type that you're iterating over. So in this case, where our list is of type double, so we're going to need a function that takes two doubles and returns a double. Then we're going to call reduce on the list with that function, and it's going to reduce this entire list to a single value by applying that function. So in this case, this takes two doubles and returns the first double, which is an accumulator value. Similar to the accumulator pattern that we've done in 115, this is your accumulator variable, and then this is the new value that you're iterating over on the list. So in this case, we're going to take this function. It's going to be called on the first two elements, where the first value of the list is the initial value of the accumulator, A in this case, and then the second value, 2 squared, it's going to return 5, and then 5 is the new value of the accumulator. We're going to call this same function on 5 and 3. That's going to give us 14. Call it same thing on 14 and 4. 4 squared, 16, 30, if I'm not mistaken. 30 and 5. 25 plus 30, we're going to get our 55, and that's what's eventually returned in this call of reduce. So we're taking one function, which is defining how to combine values, and then collapsing or reducing this entire list into a single value by applying that function. So like if we just did A plus B here, we would get the sum of all the values in a list. If you had a question, hey, or just a spot in your code where you need to sum the values of a list of doubles, you could just give it the addition method, numbers.reduce, and you could actually do underscore plus underscore. We'll get to that in a second, and get the sum of that list with no worries. I forgot my close paren. That bugs me. Notice that this example does break. This specific example breaks if 1 is not the first element, because 1 never got squared. But since 1 is its own square, we do get away with it in this example. So the accumulator is initialized at the first value. That's okay because it's 1, but the first value does not have whatever functionality you have going on applied to it. So you can use the shorthand of underscores even when you have 2 input parameters. If you use this, you have to have 2 underscores in your function, and the underscores have to be in the order in which they appear in the function. So they have to match the order of the parameter list. So the first parameter is the accumulator. So the first underscore that appears is going to be the accumulator, which was A in our previous example. The second underscore is going to be the current value that we're looking at the list, which is the B in our previous example. But you can use this underscore shorthand even when you have 2 parameters, but their appearance in the function definition has to match their appearance in the parameter list. So here we're expected to have accumulator, then value that we're looking at. So that's the order that they have to appear. If I did math.pow underscore of 2 plus underscore, I'm going to get completely different results. I'm going to get the wrong result according to what I'm trying to do with this method. I'd be keep squaring the accumulator instead of squaring the current value I'm looking at. And we can do that if we have like just time multiplying 2 things, like we could have done in the previous example. If we were just adding these, we'd do underscore plus underscore. And that's a completely succinct, boiled down way to take the sum of a list of numbers. Or if we want to concatenate a list of strings, maybe we want to do something like that. Very succinct, very short syntax for that. If you're interested in reducing your typing. Like here, we say we want to take a list and multiply all the values of the list together. Underscore times underscore, donezo. Accumulator times the new value we're looking at, and keep going through the list and collapsing it. So with this one, we're using fold instead of reduce. There are a few differences with fold and reduce. They're mostly doing the same thing. They're taking a function and collapsing the entire data structure based on that function that takes 2 inputs of the type of the function. Except we have 2 major differences here. One, we give it an initial value. Fold takes an initial value as a first parameter list. We have 2 parameter lists here, so new syntax too. But we set an initial value. Here, since I'm multiplying these together, I want the initial value to be 1.0, the multiplicative identity. And then this will be the first value in the accumulator. And then we actually do have our logic applied to the first element of the list. So if we wanted to sum the squares like the previous example, and our list didn't start with 1.0, we could use fold, give it an initial value of 1.0, and then underscore times underscore squared. We could actually get that functionality using the fold method. So we get an initial value, and the function is applied to every element, including the first one, outside of our accumulator, where before the first element was the initial value of our accumulator. The other difference is that we can actually change the type of the data using a fold. So we can have the initial value. We can have the initial value that doesn't match the type of the list. This isn't something we can do with reduce. So say we want to sum the lengths of the strings in a list of strings and return that sum of lengths. We can give it an initial value of int. The type of fold left is going to be inferred, in this case, by that input. This is an int, so it's going to assume that we're returning an int. Plus, we store in a variable int. Scala figures all this out. Underscore the accumulator initialized at 0, and then plus the length of the value that we're looking at. So 0 plus the length of 0, which is 4. 4 plus the length of 1, which is 3, so 7. 7 plus 3, 10 plus 5, and we get our 15 out of that. We can also, if we want to go on the other end of the list, say we want to start at the end and go backwards, we can use fold right. So fold is going to default to fold left. Fold right if we want to start at the other end of the list, And now the parameter order is reversed if we're using fold right. So it's the value of the list and then the accumulator. So we do have to reverse that if we're using fold right. So if you want to start at the end of the list, for what it's worth, if you ever have a situation where you want to do that, reverse the parameter order. And we're kind of out of time, but I do want to go to IntelliJ for this. I guess it's technically not part of the lecture, but I do want to give this polynomial example. This was pulled from the genetic algorithm homework. I used to use polynomials for that. I switched it to lines for this semester just to hopefully reduce some of the confusion. But I still want to show you the polynomial code for this, of how to build a polynomial and use these functions to get stuff done. So here I have a class polynomial that takes its coefficients as a list of doubles, starting with the highest order term and then ending with the constant. So if these coefficients are list 1.5, negative 2.2, and 5, that's 1.5 squared minus 2.2x plus 5. So that's the way we're representing these polynomials. And I want to evaluate a polynomial without using var. So I'm going to use some good old functional programming. If I want to evaluate this polynomial at x, what I can do is call reduce. I have my accumulator, which is going to be all of the collapsing of this polynomial, evaluation of this polynomial so far, and then the current coefficient that I'm looking at. And I'm going to start at the beginning of the list. I'm going to reduce, defaults to reducing from the left and iterating forward through the list. So I'm going to have 1.5 times x plus negative 2.2. So I have 1.5x plus, or minus rather, 2.2. And then I'm going to move on to the next value. I have whatever that evaluates to, which is 1.5x minus 2.2, and then 5. So the accumulator is going to be multiplied by x, which gives me 1.5x squared minus 2.2x plus 5. And I've reached the end of the list, so I'm going to return that. So here's a way where I can evaluate this polynomial by creatively using this reduce method, by always multiplying whatever I'm accumulating by x. So no matter what the degree of this polynomial, that first highest order term, each time I go through this reduce and look at a new element, it's going to be multiplied by x again. So if I have like an x to the fourth and then 4 more parameters, 4 more coefficients, that first one is going to end up being multiplied by x 4 different times as we go through all the other parameters. So I can collapse an entire evaluation of a polynomial into this. And if I shorten my parameter names, or if I eliminate them completely, we can get that all the way down to this. Oops. You can evaluate a polynomial with like no code. I would argue that this is a little bit unreadable. So I do like, this is one case where I would expand it without the underscores. But you could get this way succinct. You can have such succinct code, such expressive code, when you're taking advantage of this functional programming ideas. And then for a cost function, so if you haven't looked at the assignment yet, the cost function for this polynomial or line in the current assignment is going to be the sum of the squared distances of a list of points to that polynomial. So for each point in this list, I want to evaluate that point, the polynomial of x for each point, and then compare that distance to the y of that point, square that distance, and then take the sum of all those distances. So for that, I'm going to use a fold left, which could just be fold. Just for clarity, fold just calls fold left. Doesn't do anything, it just calls fold left. And fold left does our actual thing and does use var internally for what it's worth. So fold, I'm going to initialize to 0. I want to get the sum of the square distances of these things. Why do I have, did I need fold left? Oh, why did I need fold left? Oh, I'll think about that some other time. That's going to bug me now. So I'm going to initialize to 0. Before I start looking at any points, the sum of the squared distances is 0. And then start accumulating as I go from left to right in this data structure. So the distance, this is my accumulator. It's the current total sum of squared distances for this list of points. And then the current point that I'm considering. So the total accumulated distance plus evaluate that point, which calls our evaluate method below. Subtract that from the y value of this point. That's going to give me the distance away from this point, the difference of the distances from the polynomial to that point. I'm going to square that. So I don't care if that difference was positive or negative because I'm going to square it. It's going to be positive after squaring. That's going to give me the distance, the difference. And then I'm going to divide it by the points dot length just so I can get the average distance. This isn't strictly necessary for our application. We could leave that off, but I want the average distance, average squared distance of all these points, just so I'm not penalized for having more points in the list. But we can get that done with a fold. And now I am curious. Officially change this to chatting. But now I am curious. Why did I need to fold and not? Why did fold left? Maybe it's messing up the inference. I think it's messing up the inference because it can't tell which one is supposed to be the accumulator and which one is supposed to be the current value that we're looking at. Oh, fold can't even. Oh, that makes sense. So if we want to change the type, we can't even use fold. So fold takes the accumulator, initial value, and everything is all the same type. This A1, which has to be a class, a superclass, or itself of the data that we're iterating over. So that's why. So fold doesn't let us change the type. Fold left and fold right do allow us to change the type. Here we have two type parameters, A and B, where A, remember we're in the list class. A is the type of the list or of the general, traversable of the data structure. We use lists in this class, and then converts it to values of type B. So I guess we can't do, that's not the same method, but you get the idea. We have two different type parameters for fold left, but only one for fold right, or for fold. Is that true with reduce? Oh, we can change the types with reduce. I misspoke on that. But we have to call reduce left or reduce right. That's the new tools learned in this lecture. Yeah, this is one of those, just here's a bunch of cool stuff you can do lectures. You know how these concepts work. Here's some cool stuff you can do with it. It's very empowering if you start using these things, which you have to for your homeworks and for the next few lecture questions. I'm going to force you to get practice with it, and hopefully by the end you realize how cool it is, and then you keep using it even when you don't have to. But if you don't, hey, at least you tried it. At least you tried it out and got a feel for it. And for a more practical reason why you should learn these things is you will be reading code that uses functional programming at some point in your career. You're going to have a colleague who uses it. You're going to be using a library that you have to dig into the source code for whatever reason. You're going to come across this stuff. Oh, yeah. Literally, I can't even. Mango Mutiny. No, you already finished the assignment, and want to see what you could. Did you Mango Mutiny? Did you use a whole bunch of different stuff to get it done? Have you mentioned how to look at the Scala functions before? I'm not quite sure what you mean, QT Bunny. Oh, the built-in ones. Yeah, I did. I do. I feel like somebody asks each time, but I'm happy to go over it again. It's a control click. Hold control, click. And you can take a look at all the source code. And there was something we wanted to... Yeah, let's look at one of the... Let's look at map, actually. And, yeah, things get harder to read, but I can't even read this without really thinking about it. Oh, boy. But we do have var. That's the big thing I wanted to show. And then a while loop, which is appending, really digging into the structure of a linked list, but appending each value. This will actually make more sense once we cover linked lists next week. But they're appending to a linked list without using the append or prepend methods. They're really digging into the functionality of a linked list. So they're creating a new element and then setting the next value, whatever t points to, which is the current end of the list. The next element in that list, they're going to create a new element for the next one, and then have that element that was the end of the list point to that next value, and then update t to be that next value. So they're creating the first element in the list, creating the next element, and then having that first element point to it, and then updating that element, then creating the third element, having that second element point to it, and then updating and iterating through like that by using this : So : is actually a class. That is actually the class name for linked lists, for a linked list node in Scala. And then they're taking advantage of the internals of that to be able to build the thing. Is tail recursion the same thing as regular recursion? No. So tail recursion is regular recursion, but regular recursion is not tail recursion. Tail recursion is recursion where the recursive call is the last thing that happens in that method. So like our min recursive function from the recursive examples on last Wednesday, this is a tail recursive function. So even my ID just says it's tail recursive because the last call is always the recursive call, and then that's immediately returned. Whenever that's the case, the compiler can flatten out the recursion. It actually doesn't put a new stack frame on the stack for each recursive call. It gives us some optimizations, which actually allowed us to build this function in a way that works. Our step size, for example, is 1. And if we don't have a local minimum, we're going to go out to one of the infinities, and I'm checking just some crazy large number. I guess not too crazy, but 10 million or negative 10 million. When I get to one of those points, I'm just going to say, look, I'm going to assume there's no local minimum, and I'm just going to return infinity. So normally this would put 10 million frames on the stack, which of course would overflow the stack. But since this is tail recursive, we don't put all those frames on the stack because there's no reason to return back to this frame. If this frame is just returning the return of the next frame, we can collapse those frames, and instead of having hit the base case, return to a frame, then return, then return, then return, then return. Since there's no work to be done in each of those stack frames, we don't need those stack frames at all. We're just going to collapse them and say, look, instead of returning, why doesn't the recursive call just return directly to the initial calling method? So why don't we return right directly to this method, and then that method can return back to the main in this case. So that's how we get away with this. We hit 10 million recursive calls, but without extra stacked frames, because this is tail recursive, because there's no more work to be done after getting the return value of the recursive call. That's not something I will test you on. If don't think about tail recursion in your labs and interviews and stuff. That's not something you need to know. And even if I do accidentally, I'll try to avoid it. But if I accidentally give you a tail recursive question, a question that's actually using tail recursion, still talk to me about all the stacks, the frames that are put on the stack. Unless you say this would happen, but this happens to be tail recursive, so that actually doesn't happen. But I do want to know that you know about stack frames. So don't just say, well, that's tail recursive, so there are no stack frames, QED. So it's fine if you just don't think about that during your stuff. But that is something that the compiler will do. It's one of the cool things compilers do for us. Yeah, like if we had recursive factoring too. Oh, yeah, recursive factorial. If I had if n less than equal to 1, else. Oh yeah, we can't do that, can we? I mean, we can, but like this is how we would normally write factorial. I disagree. What? Oh, I didn't give it a return type. Jeez. I need to go back to week 1. So this is not tail recursive. We get a different symbol here. And it just says it's recursive, not tail recursive. There's actually an annotation. If we expect something to be tail recursive, we can add this annotation so the compiler checks and makes sure that it's tail recursive. Which is nice because then the compiler gives us an error if it's not actually tail recursive. So if you expect something to be tail recursive, it helps to add that annotation. And here we're going to get an error because it's not actually tail recursive. This isn't actually tail recursive. If we did, since we're here, I'm not sure exactly how I want to do this. I think like this. Helper. And we can get some good old tail recursion. Oh, that's certainly going to overflow an int, but we'll get at least some value out of this. Yeah, I'm probably overflowing an int many, many times there. Nope, I'm just wrong. No, I'm not just wrong. Oh, it's already 4:42 time. I want to finish up this thought though. Right, 4, 12, 24. Yeah, okay, so I'm right. If we do like 10,000, we're just overflowing int so many times. It's just breaking. But if I undo, paste, run, we're going to stack overflow because this is not tail recursive. Oh, come on. Don't make me a liar out of me. Why not? Tutorial. Oh. No. Well, I don't know. I get it in the debugger, but something's shortcutting this and just returning 0. Which has got to be just from overflowing. But if we avoid the overflow, I don't know why it would just shortcut to 0. That's strange. You ever want to know what 500 factorial is? It's a stupid big number. And for those of you wondering, worrying about overflowing your stack, like you're not overflowing your stack unless you're doing something ridiculously silly. Usually only if you have infinite recursion. But I can get thousands of frames on the stack, and it's no big deal. I'm actually surprised it's going this high. And I got to overflow the stack because it's 442 time. I'm already cutting in. There we go. There, we're overflowing the stack. Yeah, it's overflowing the stack is not something you have to worry about unless you're really breaking things. But if you are worried about that, if you're in that region, tail recursion is your friend.